Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today, I am going to introduce a method to evaluate the definite integral of the form integral 0 to 2 pi f of cos theta sin theta d theta. That means the integral of a function which is involving sin theta and cos theta terms. So, the overview of today's presentation is to evaluate the real definite integrals by contour integration. Contour integration means simply evaluating the integral along a curve, which is a closed curve. These integrals arise in physical problems, and in such cases it is suggested to use the residue theorem. So, the evaluation of real definite integrals arises in physical problems, and in such cases it is suggested to use the residue theorem. What is the residue theorem? Using the residue theorem, we can evaluate the line integral of a function f of z dz along a curve C using the residues. So, 2 pi I into sum of the residues, that is residue theorem. Now, today we are going to discuss about a method of evaluating the line integral of a function which is having either sin theta or cos theta terms. And here the integration is around unit circle, that means mod z equal to 1. So, here the procedure is, we consider z equal to e power I theta, and using this transformation we transform the given function which is in terms of theta to z, and then we find the residues, and using the residue theorem we can evaluate the line integral. So, integrals of the type 0 to 2 pi f of cos theta sin theta d theta, where integration is around the unit circle. So, here the method is put z equal to e power I theta. So, let us consider z as e power I theta. That implies differentiating on both sides, we get dz equal to e power I theta, derivative is e power I theta, and the inner function derivative is I into d theta. And since the function is in terms of theta and here we have d theta, we need to transform d theta to dz. So, let us calculate the value of d theta, dz by I e power I theta, but e power I theta is z, so dz by iz. So, we use this transformation and we replace d theta by dz by iz, and also we have the expression for cos theta. What is that? E power I theta plus e power minus I theta by 2. Similarly, sin theta is e power I theta minus e power minus I theta by 2i. So, we use these two transformations and we transform the function of theta into a function of z. So, later the theta varies from 0 to 2 pi. So, this integration becomes along the curve C of a function of cos theta. What is cos theta? 1 by 2 e power I theta plus e power minus I theta plus 1 by 2i e power I theta minus e power minus I theta, this divided by so this is into d theta is dz by I e power iz. So, this is the given line integral, and now to evaluate this we take the help of residue theorem. So, first find the residues of this function, at the poles which are inside the curve C. So, we find the poles and then identify which are inside C, and then residues, and finally use the residue theorem to evaluate the line integral. So you will get a clear idea if we discuss a problem on the same. So here, show that by method of residues, integral 0 to 2 pi d theta by a plus b cos theta equal to 2 pi by root a square minus b square, where a is greater than b is greater than 0. Now coming to the solution part. So here the integral is 0 to 2 pi d theta by a plus b cos theta. So this is LHS. Now we need to prove that this integral value is equal to 2 pi by root a square minus b square. Now as usual, the method, we follow the method. So replace or use the transformation z equal to e power I theta. That implies dz is I e power I theta d theta. So d theta is dz by iz. And here the function is involving cos theta. So cos theta equal to e power I theta plus e power minus I theta by 2. So which is e power I theta is z. So z plus 1 by z by 2. So which is z square plus 1 by 2z. Then the LHS becomes along the curve C, here 1 by a plus b into cos theta is z square plus 1 by 2z into d theta is dz by iz. Now this 1 by I comes out and integral C. Now simplify this. Here the LCM is 2z, that comes to the numerator, 2z by 2az plus bz square plus b into dz by z. So these two gets cancelled. So 2 by I, this is equal to 2 by I along the curve C, 1 by bz square plus 2az plus b dz. So which is in the form of some 2 by I into integral C f of z dz, where f of z is 1 by bz square plus 2az plus b. So the given function, which is in terms of theta, is transformed to a function of z, and we need to evaluate this line integral. And here the poles can be obtained by equating the denominator to 0. So bz square plus 2az plus b is equal to 0, which is in the form of ax square plus 2ax square plus bx plus c equal to 0, a quadratic polynomial. So the roots can be calculated using z equal to minus b plus or minus root b square minus 4ac by 2a. So z equal to minus 2a plus or minus, here root 4 comes out, 2 root a square minus b square by 2b. So again simplifying, this becomes minus a plus or minus root a square minus b square by b. So these are the poles of this function f of z. And here we are using the unit circle mod z equal to 1. So C is the unit circle mod z equal to 1. Now we need to identify which pole is inside this curve and which is outside the curve. So here z is minus a plus or minus root a square minus b square by b. So the roots are minus a plus root a square minus b square by b and minus a minus root a square minus b square by b. Let us denote these two roots by alpha and beta. So alpha is minus a plus root a square minus b square by b and beta is minus a minus root a square minus b square by b. And given, what is the given? The condition is a is greater than b is greater than 0. So a greater than b greater than 0. That implies here beta, the mod beta is greater than 1. And also we know that the product of the two roots alpha into beta is 1. So mod alpha into beta is 1. So therefore mod alpha into beta is 1 and mod beta is greater than 1. That implies mod alpha is less than 1. So therefore this alpha only lies inside the circle C. So here alpha is only the pole. Alpha is only the pole which lies inside the given circle. So we need to find the residue of F at Z equal to alpha. And here alpha is a simple pole which is repeated one time only. So which is not repeated simply. So alpha is a pole of order 1. So it is a simple pole. Now we need to find the residue of F at Z equal to alpha. What is the formula? Residue of F at Z equal to alpha is equal to limit Z tends to alpha, Z minus alpha into F of Z. So limit Z tends to alpha, Z minus alpha into 1 by that F of Z can be written as B into Z minus alpha into Z minus beta. So here these two gets cancelled, and by taking the limit as Z tends to alpha, this is 1 by B into alpha minus beta. And we have alpha is minus A plus root A square minus B square by B, and beta is minus A minus root B A square minus B square by B. So alpha minus beta becomes minus A by B plus root A square minus B square by B minus, so this becomes plus A by B, and again this becomes plus root A square minus B square by B. So these two gets cancelled, and here 2 root A square minus B square by B. So therefore the residue of F at Z equal to alpha is equal to 1 by B into 2 root A square minus B square by B. These two gets cancelled. So 1 by 2 root A square minus B square. And by residue theorem, the line integral of a function f of z dz can be obtained as 2 pi I into sum of the residues. So using this, we can evaluate the line integral of the given function. So the line integral of this function 2 by I into f of z dz is equal to 2 by I into 2 pi I into sum of the residues. We got only one residue, 1 by 2 root A square minus 1 by 2 root A square minus B square. So here this 2 gets cancelled, I gets cancelled. So 2 pi by root A square minus B square. So 2 pi by root A square minus B square is the RHS. 2 pi by root A square minus B square, which is RHS. Hence, the line integral from 0 to 2 pi d theta by A plus B cos theta, A plus B cos theta is equal to 2 pi by root A square minus B square. So using the residue theorem, we can evaluate the line integral of a function which is having either sin theta or cos theta. Similarly, to prove this, integral 0 to 2 pi d theta by a plus b sin theta. Let us use sin theta equal to e power I theta minus e power minus I theta by 2i, and z is e power I theta. So d theta is dz by iz. The same procedure, if you follow similar procedure, we can prove integral 0 to 2 pi d theta by a plus b sin theta is also equal to 2 pi root a square minus b square. So the same procedure you need to follow to prove this, that you can practice. And here sometimes the problem may be asked in the form of 0 to pi d theta by a plus b sin theta, or 0 to pi d theta by a plus b cos theta. And since this function here, this let us solve these two. Evaluate the line integrals. The first one, integral 0 to pi d theta by 3 plus 2 cos theta. So we have 0 to pi d theta by a plus b cos theta is equal to 2 pi is equal to 2 pi by root a square minus b square. So here, by comparing these two, a equal to 3 and b equal to 2. So 0 to pi d theta by 3 plus 2 cos theta equal to 2 pi by root a square 9 minus b square 4. So 2 pi by root 5. And coming to the second one, integral మళ్ళీ ఇది రిపీట్ చేద్దాం. Escape. Coming to this third problem, here we need to evaluate integral 0 to pi d theta by this one and 0 to pi d theta by 1 plus a cos theta. So first one, or first we have, what is the previous one that we have proved? 0 to 2 pi d theta by a plus b cos theta is equal to 2 pi by root a square minus b square. And this can be written as, or using this, we can evaluate this 0 to pi a plus b cos theta is equal to half 2 pi by root a square minus b square. So these two gets cancelled and pi by root a square minus b square. Now the first one, integral 0 to pi d theta by 3 plus 2 cos theta. So comparing this with this, a equal to 3 and b equal to 2. So therefore this value is equal to pi by root a square 9 minus b square 4. So pi by root 5. Similarly, the second one, 0 to pi d theta by 1 plus a cos theta is here a equal to 1 and b equal to a. So pi by root a square minus b square. Pi by 1 root 1 minus b square. So in today's session, we have introduced a method of finding integral 0 to pi or 2 pi, a function having sin theta or cos theta or both. And for this we use the residue theorem. First we transform this function of theta to z, and then we find the poles and identify the poles which are within C, then find the residues, then use the residue theorem to evaluate the given integral. So this is for today's session, and in the next session also we will continue the same model. Thank you.